I know that most of you probably have never really worked with 3D. So quickly for introducing myself, my name is Madlaina. I'm a game designer, so if you want to talk games, you should come to me afterwards. And I'm also a full-stack developer, which makes me kind of this generalistic thing that likes to do everything and also be artistic. And so seeing the problems that developers have if they want to get started with webVR or 3D is that they actually don't really have an idea on where to get started. So my mission is to make 3D content accessible for everyone. And also my question was yesterday, how can we actually make 3D content accessible for all consumers? But today we're only going to talk about making 3D content available for developers. As I said before, I love games, I want to talk games, but I also like other things like traveling, technology, creative things. Yeah, it's so many things that we can do in this world. Why should I use 3D? Why do I even care as a web developer or as a developer? What can this even give me? It's a good question because I think the easiest answer to that is that humans are spatial thinkers. So if we have an environment, we always connect spaces with information. On the web or with most of applications, we only have a two-dimensional representation, though, of this. However, with webVR, AR, and mixed reality, we can now go into this space and actually map our information to different locations, which is, for example, the sound that Monica was talking about before is just one single thing. Because we as humans, we care about where the baby sound is coming from. This is so much fun when you kind of hear everything and you just want to know what's going on. And other than that, we can make really fun games. Games is something that everybody enjoys. You might disagree, but you have been playing since you were little. Everything you learn in the beginning of your life is through playing. And also animals do it. So this game is by Ada. Check it out. It's so much fun. I can only recommend it. And it's also made with A-frame. And also, as I said before, spatial information is super interesting because it helps us understand information better. So if you want to visualize your big data or all your information that you have, with the third dimension, it actually gives you it gives you literally another dimension on what you can show, which makes it super interesting. For example, in this example from Visicities, they also used the third dimension to show where something's happening, and they also used the fourth dimension, so they used time to show how information progresses over time. I think this is a really big deal in the future to also understand things better, because what we have been doing at Archeologic, so I also worked at this company before, what we have been doing is trying to show people what they can do with their apartments and how they can furnish it and actually understand this underlying floor plan that is super cryptic and nobody understands it and nobody can imagine how the space looks like. I want to talk a little bit more from the designer's aspect and get you started on 3D. You have learned now how to do 3D with A-frame, and I sure hope that everybody's going to go home and try it out. I want to give you a little bit of a tool set, though, on how to get started. Because you're going to hit a block at some point, and I want to be already aware of when it's coming so you can jump over it. Therefore, I would like to talk a little bit about the physics of light, because we are now in the third dimension. And you can imagine if you have a blank sheet of paper and you don't have anything, how do we even see things? Because, for example, now I don't see any of you because I just have that light shining at me, which is kind of a shame. But So the physics of light, we see here in this frame, we have a little 3D scene, and it has a sun outside, and we have a table and a laptop and a chair and some shelves. What's happening now is that the sun, or any light source, is shooting a ray. We're only tracking one ray for now, otherwise it gets a bit complicated. It's shooting rays down to the Earth, and what happens is these rays are electromagnetic waves that interact with objects' materials, so that the surface texture of the object actually influences on what happens with the light. So the light rays bounce off, and they kind of bounce around in the scene. They hit the chair, and then at some point they lose all the energy, and then they're gone. Or they actually bounce into the retina of your eye, which makes then the ray visible. So, as I said before, these waves are also made up from frequencies. And many, or maybe some people of you know that frequencies are basically just, the range of the frequencies make up the colors, which is pretty interesting when we talk about colors later on. So what we actually can see are the rays that hit our eyes. So there is many rays that we will never see, because the sun shoots millions and billions, and I don't even know how many suns per milliseconds shoots so many rays, so we kind of lose most of them. The materials, surface textures, they actually, so how it works is these waves are bouncing off the objects, and some of these frequencies get absorbed. Some of them get reflected, like in these really pretty balloons that I love so much, and some of them get transmitted. And I want to talk about that a little bit more. And you're going to wonder, why is she telling me these things? So with materiality, we have 3 basic concepts, and they are super, super important for when you do 3D. The first one I would like to talk about is specular reflection. So you can see we have these rays of light that are coming, and if we have an object like a perfect mirror, it will reflect those rays all uniformly, which then creates this mirror image, so we can actually see ourselves, because the ray doesn't get absorbed, it just gets basically transmitted, and we can see what the ray that comes from us goes in, right? So the second one is diffuse reflection. This is mostly material like cloth or tissue or strings or anything that basically is not shiny. So what happens is the rays enter the surface and they get scattered around like crazy. So you can still perceive it, but there is no uniform reflection, so you don't see yourself in it. And then we have propagated light. This happens when the material doesn't only reflect, but also lets through some of the rays, which is refraction. It's called refraction, and it's basically the reason why we can, for example, have houses with glass windows, because otherwise we would just sit in the dark if there was no propagated light. And usually you could say that these 3 concepts, it's not everything that makes a material, but with these 3 components, you can basically create most of the materials that exist in this world. Like you can create a fake representation of it, like this. And the interesting thing about this is that usually the materials are so complicated that it's really hard to kind of get a grasp on how do I make a fake wood floor. Because you have the wood the surface texture is rough, so you basically have a diffuse reflection, as we saw before, so it scatters it around. But if we have a parquet floor, we also have a really glossy finish on top of that wood, which makes it glossy and shiny and reflective from certain angles. So we really have to be aware when we do 3D. If we want to create a realistic or good-looking imagery, we have to be aware of what our materials look like, because there's a really great, amazing variety that we can achieve, which makes it more realistic, which makes it more immersive. Or if you're more of an artistic person, like Monica, you said you're not, but if you're more artistic, then you want to use the knowledge of these concepts to make your scene more artistic. So how do we actually get 3D on our 2D image? That was the question I was asking myself, when I was asking myself, how can I make this more accessible for people? So one of the first cameras, this is very widely known, was a pinhole camera obscura. Basically, you have a light-sensitive surface on the back of a box, and in the front of the box you have a really tiny hole. And this tiny hole allows basically one ray of light per pixel, let's say pixel or per surface point on this sensitive filter to enter the box. And this creates a static image. So for 3D, we actually have a quite simple or similar approach, and that's the ray tracing technique. Ray tracing, we can really break that down and say, we don't want to trace the rays from the sun, because we lose that many, but we actually want to do it backwards. So we start from the camera, and we go through every pixel of our image that we want, and we shoot the ray from there into the scene. And then we check every object in the scene, there's only one right now, and see if it gets hit or not. If it gets hit, we have to see if this object is actually illuminated or not, so we cast a shadow ray, and if there's nothing in the way, then we have sun, and if there's something in the way, we have shadow. Now, but with materials, this gets a bit more complicated. So here in the middle you see that there is a sphere that actually has transmission but also reflection. So we shoot our primary ray and it hits this sphere, which is transparent right now. And now what happens? We have to split up the ray because parts of it goes through the object and the other part goes to be reflected. So we cast the reflection and the refraction rays. And from there we see if there is an object being hit by that ray. Because it depends if the reflection ray is hitting this this red sphere, then that's the pixel that we see in the end should be red. But it also hits this, the refraction ray also hits this green sphere. So we need to have a mix of green and red. Now, however, we don't know if these red and green spheres are in shadow or light. So we cast the shadow rays from there on. Sounds easy, right? So Patricia has been talking to us yesterday about reading code. I'll drink some of my tea. Please go. You can explain it to me later. So actually, this is a really common problem or like challenge that computer graphics people give themselves. It's how to write the shortest ray tracing code that fits on a business card. So this is can be actually written on a business card. And I was in Iceland and there was a presentation from Martin Kleppe, I think was his name, and he was telling me that somebody did it in 149 characters. So I'm a bit sad now, but this is not my code anyway. So I tried to break this down a little bit. We are now, for this simple implementation of the ray tracing technique, we're just focusing on rendering primitives that we have talked about before as well. So we actually are only looking at spheres because this is the easiest primitive to actually mathematically work with, because basically we just have to know if our hit is in the radius or not. So what we want to do for each object that we would have in our scene is to actually have an intersection function where we check if the ray that we are shooting is hitting the object. So if it's missing the sphere, or if it intersects with it. And if it intersects, it means that it has an entry point and also a point where it goes out of the sphere again, because that's what we're going to need for refraction. So we define our scene, and this is not as elegant as in A-frame. So we put a few spheres in. I didn't put any, for abstraction's sake, I didn't put any positioning or anything. It's just to illustrate you what we have to do to actually get the rays. And then for each pixel in our canvas, we're going to trace one ray. That's going to look like this without all the math. So basically, we shoot the ray and we're going to go through every object in the scene, which makes it so computationally heavy. We have to go through every object in the scene and check if there's an intersection, and then we take the closest intersection object that we can find. If we don't find anything, we just take the background color because we don't have anything there. If then the material of that nearest object is transparent or reflective, we're going to do the calculations of the refractions and the reflection rays. And we're going to use a mathematically weighted function to calculate them together and return the pixel. So then we're going to have something that looks like this. It's slightly realistic because we have the reflections from the spheres on each other and things like this. We have shadows on the floor, but it doesn't look good, actually. So the problem is with ray tracing, while you can implement, and that's kind of the point of this talk, you can implement it in any language, in any tool, as long as you have a display for showing your results, pretty easily. The code is super simple, but as soon as you want to get actually more realism, which means, for example, you want to have multiple rays per pixel, because if you have one ray per pixel, you're going to end up having a problem when you start moving the camera, for example, because of aliasing and things like this. So you're going to have to think about that and shoot multiple pixels and then have adaptive supersampling and all these fancy terms. So it's easy to get into if you want to play around and kind of know what this is. That's what I was doing because it was helping me to understand how we actually do render things. And the other problem that we have, it's already showing here, what do we do if you have multiple light sources, for example? What if we have complex geometries that are more organic or just beyond the simple spheres that are easy to calculate? But what do we do with actual transmissive materials that are maybe like milky or just a bit more complex, if you have milk glass or something? And the biggest thing is this basic ray tracer that I was showing is actually not physically correct, which is the biggest plus point of using ray tracing is that you have, because you take the light's physics concept, you actually get a physically accurate result. But we take a shortcut here because we just see, are we hitting the sphere, is it in shadow or not? And that's not what happens in real life, because in real life, it's just bouncing around, and we have so many rays that bounce around that some of them will hit our eyes. So that would lead me to explaining what path tracer is, and then the day is over. So path tracing basically means, very short, that we actually just shoot the rays and see when will the ray hit the sun or the light source. So we make them bounce around as long as we can, which is more and more and more and more calculations. So I'm going to ask you later on how long it will take us to do ray tracing in real time. And this technique is pretty old. It's like one of the first 3D techniques that I have been finding online. Also, if you have this many, if we have a lot of objects in the scene and very little light sources, we're going to end up with a lot of noise because probably we're not going to find our light source. And yeah, the problem with how do we weight if we have multiple lights? How do we even do that? So actually, I would like to also kind of shortly introduce a second and more common real-time render technique, which is rasterization, and most of you probably know how that's working. And that's also what A-Frame is doing in most computer games. So it's just as a fundamental technique as ray tracing, because ray tracing is used for static rendering. And it solves the visibility problem of the objects in the scene in quite the opposite way of ray tracing. So while ray tracing is going from the eye through the 3D scene and has like understanding of what the 3D scene is and what are the relations of the objects to each other, the rasterization techniques takes the objects to the eye by actually using perspective projection to flatten everything onto your canvas. And then it's trying to figure out in the screen space which of the primitives are in front of each other. So for this, we are using polygons, triangles, because that's the most simple primitive that we can calculate, because triangles are always planar. So we basically just see what is in front of each other, because basically we can abstract it to 2D. Right, I'm going ahead of myself. So when we have all the triangles in the raster space, we kind of have information about the depth of these fragments. So we can see which pixel, which fragment lays on which pixel, and if there's multiple, then we kind of layer it with the C buffer. This is, in the end, how we do mostly the 3D graphics in these days. And the crazy thing to me is that it's actually absolutely impossible to do any physical correctness. Therefore, in my opinion, it's really hard to get it look realistic. And that's what you have to kind of know. So these are two implementations, one basic ray tracing implementation and one basic rasterization on top. And you can already see that with ray tracing, you have a lot of things that come for free. For example, interreflection, so an object reflecting on itself. That's something you don't get in rasterization because we lose the information about the 3D scene. You get in ray tracing, you get anti-aliasing for free if you do a lot of sampling. You get caustics, which is if you have a transparent material and it's gonna basically do the caustics on the floor, so the reflections. I don't even know how to explain this, sorry. I'm not gonna try it anymore. And you have soft shadows with ray tracing, because basically, since you know each pixel, how many light sources are shining on that, you can make it soft. While with rasterization, you can do these things, but you have to do a stencil shadow buffer that tries to make shadows which are always hard shadows, which means there is no different grayscales inside of the shadows. So even though the rasterization techniques, if you have been playing any games recently, is super advanced. We can simulate a lot of things with rasterization. It gets really complex really quickly, so I don't think that there is one person who can write a rasterization engine that can do all these fake reflections, fake shadows, and that together. So it's good to also have an idea on how these things work. This is just a quick overview. I have covered this. I kind of have to hurry up a bit. So rasterization is fast. We have the tooling and hardware support with WebGL, and of course, OpenGL, it's physically incorrect, and therefore we have quality loss. Ray tracing is physically correct, has very high details, can be very realistic, but it's very computational heavy, and I'm not sure if with web workers and WebGL and having better graphics card, if we can actually reach the ray tracing in real time. It would be fantastic, but and there is also approaches to do that. But as soon as your scene gets very complex, you have a much more complex and slow algorithm. A-frame would be something I would now suggest you to try out if you want to get started with 3D. However, that has been covered and you're good to go. Therefore, I would like to talk a little bit about challenges. And I know it's kind of sad because I don't want to be the negative sim, so I'm going to cheer you up later. If you have no 3D content, you're not going to really have a lot of webVR that you can do. You can work with 360 degrees videos or 360 degrees images, but it's really hard to make things interactive. And as a game designer, I'm all about the fun and play and interactivity. So now I'm going to go a bit into science. So I'm going to talk about the 3D Content X truth table. And it's science because I made it myself. So we have these 4 things. How do I get my 3D models? Do I have time? Do I have money? Or I have no money and I have no time? So if I have time and I have money, I'm going to hire a 3D artist because good artistry is going to take some time. If I have no time, but I do have money, which is really a shame, because I think time is more valuable, you can go to a 3D warehouse and buy your models online that have been made by artists. However, you have to be aware that other people are also going to buy these assets and are going to use them as well. So for your corporate identity or visual identity, this is maybe not the best idea. So if you have no time, if you have time and no money, you're going to learn to 3D model. I'm going to talk about that later. And if you have no money and no time, that's the worst thing. You can go for curated and optimized content platforms like Google Poly, for example, or Archeologic's 3D.io, which can provide you with all these models that you can use to play around. And I think actually to just get started and play around, this is really fantastic, because who wants to start 3D modeling? And it's going to look like this. So you can just browse through some 3D models with A-frame and basically put things together the way you want and the way you think it looks cool, and then you play around. It's always the most fun to learn. Or, who wants to start 3D modeling? No one? 2, 3, 5? Okay. But I can't do it. That's what I usually hear. Like, I really tried. I opened Blender once, and it was so horrible, and the user interface and whatever. So yeah, I feel you. I've been there. There's a lot of questions when you have to think about getting started. What am I using? SketchUp, Cinema 4D, Blender, 3ds Max, and what format should I use? Should I go for GLTF, OBJ, FBX, whatever? I don't even know. So don't despair. I have been giving 3D modeling courses to children, and even though it's super frustrating, you have to just get yourself to do it. Just be persistent. And I don't really know how to give you the best advice, but I think it's embracing the actual challenges of the UI, for example, for Blender. But I have also done this with my colleagues at work, and after 2 or 3 hours, everybody was able to do this ducky. So yeah, I hope you find the motivation to get started. Because actually there is not that many things to consider. I think these are these are going to be the most important points on how to make 3D assets that are actually performant on the web. So you have to look at your polygon count, which means the least, the better. So best is to have a box or something. So back to the primitives. You have to be aware of your materials, and we have talked about this before. So now you know why materials are so important, and then you can enhance your materials with textures, and you can add colors to it, and you can make it really spacey, and then you'll find out that without actually having a light setup in your scene, you're just not going to see any of this work. Because without lights, there is also no 3D. You're going to know that visual identity is going to be important. And to go back to the textures, so this is a really optimized 3D model with little polygons. You add a normal map to it, and it's going to look like real, like it's real, because that's one of the best techniques from game development that I can tell you to look into. So it's definitely possible to have little polygon, but still a very pretty model. And as Monica said before, don't forget about rotation, translation, and scale, because you always want to have the origin of your object actually within the object. And it's going to make it easier after you export. If everything's correct, it's going to make it easier to work with it in webVR. And as I said before, the lights is what's going to make your scene like break or work. Because if you have very little light, or if you don't care about your light setup, it doesn't matter what you do with the materials, because everything's going to look flat. Then there is lots of ways to optimize your content, and I could talk about that for a really long time. But what I want you to actually take home is that there has been 30+ years of game development, and all these people have really done crazy things and developed crazy techniques on actually making stuff look realistic, even though it has to be super performant. It has to fit on a diskette or a CD or all these old game things that have been there. So actually making things performant is not a new task. It has been done before. So there is already my last few things. Models, materials, and lights matter. Ray tracing is super cool. I love ray tracing. But it's just not something that we can do in real time in the near future, I think. Even though people are doing really cool demos, as soon as you move the camera, you have to re-render everything, and that's going to make it noisy if you have an animation. And takeaway 3 is 3D modelers, artists, graphic designers, they do really hard work, and they have been studying these things. So there is no exposure bugs. Please pay your artists and value their time and their experience. Thank you very much. It was really a pleasure to be here. Thanks for the tea.